Okay, so hello everyone. My name is Antonio Ríos-Vila, and today I'm going to talk about my recent work, which is entitled End-to-End Full-Page Optical Music Recognition of Monophonic Documents via Score Unfolding. So before talking about the method implemented in this paper, we have to understand a little bit its motivations and understand how full-page optical music recognition is being dealt currently. So typically, full-page optical music recognition systems on end-to-end pipelines work with a two-stage pipeline, which is based on layout analysis for extracting from a music page all the music steps that are contained within, and then to train an end-to-end staff transcription system that obtains the textual representation for each single step that it is present in the score. To obtain the complete transcription, we obtain a concatenation of those transcriptions, and then we have the complete representation of the content of the music score. Although this system has proven to be very effective, it has some disadvantages. First of all, we need to train two independent models for achieving this task. One model for layout analysis for extracting all the steps that are present on the score, and another one for music transcription. And they have to be done separately and be joined into a pipeline for prediction. So we have to assume an accumulated error between them. If one of them fails, for example, the layout analysis avoids one of the music steps, then the transcription system won't work well on the prediction part. And for the other side, we have a data labeling issue because we have to define a bounding box for each step and then write down their corresponding transcription for each labeled step. So all corpora have to be manually labeled twice. So in this paper, what we try to do is to join both models in one single step to prevent these inconveniences. A graphic that shows this, how our approach is compared to the state of the art, it is this one. So our goal is to achieve what it is shown below in the image, which is a single end-to-end transcription model that it is trained with only pages and transcriptions, and directly from an input image obtains the complete page transcription. To do so, what we do is to extend the OMR transcription system that is currently done. This, just for refreshing it a little bit, it's a neural network that it is composed of a feature extraction part, which is fed with a music stuff. And then to convert from an image domain to a sequence domain one, it is perform a vertical collapse where we obtain that sequential representation of all the frames within the image. As we understand that each frame, column-wise pixel data, it represents the same symbol. And then we use a decoding stage, and all is trained with the CDC loss strategy. So what the network learns, it is to correlate the textual representation of the music stuff with all the column-wise features, which are called frames. In this image, for example, we see an example that there are some frames that represent a symbol, as it has also been shown in the keynote of the workshop. However, in full-page images, this cannot be directly applied because we have several symbols that are not sequential in the music score that coincide in the same frames. So we do not know what to predict in which time step because we have collision of music notes. We could use a strategy where we can use few frames for each symbol, but that would be also wrong because we are not correctly extracting the reading order of the music score. So we won't have a correctly ordered sequential music representation of the content of the music page. So in conclusion, the current end-to-end approach does not work for full page. In our case, what we do is to work in the transformation within image domain and sequence domain. We do what we call a score unfolding approach, which is by working with the feature, the features extracted for the feature extraction module, we obtain a feature map. And what we do is to sequentially concatenate all the rows from this feature map. So we try to make the network to learn or to implicitly learn to align each music stuff to one row of the feature map, then concatenate them and as all of them are concatenated, we can have a sequential representation or textual representation of the full page that can be trained with the CTC loss function, as we are able to correlate a sequence or a continuous sequence with the unfolded version of the music score, which is indeed how it happened, well, how monophonic scores are usually read. To do this, we implemented 3 models. One was a sequence processing free approach, where we have only a convolutional neural network for our feature extraction, and then directly our reshape and linear classification. Then we have the convolutional recurrent neural network adaptation for this model, where we have an LSTM approach for the sequence processing module and with our reshape. And then we also included the transformer encoder, as we thought it was an interesting approach to also evaluate, as sometimes in music pages we can find a lot of symbols, and recurrent neural networks could underperform in these specific cases. We used 2 datasets to evaluate our approach. Both are 2 real datasets of monophonic mensural music notation. One is in printed engraving, which is in Lauro Seco. And the other one is the Capitan dataset, which is handwritten one. Indeed, I must note that there are few samples for them, only 100 samples for the Lauro Seco and 90 pages for the Capitan dataset. So we also evaluated how data augmentation could benefit our could benefit our approach for training. Also, we do it for measuring our performance. We use the average symbol error rate, which is an edit distance-based metric, which represents the amount of error that it is being produced in a transcription performed by the model. So the lower this metric is, the better. So I show you here the results obtained. In the graphic on the left side, we have the in Lauro Seco results, and on the right hand graphic, we see the Capitan ones. As we can observe, we have compared our models with the baseline of the document analysis and single staff transcription module, which are not directly comparable because there are some advantages document analysis and single stage transcription have, as they have more samples and also have fine-grained data, while our approach only uses weakly labeled data, which is only the pages and the transcriptions. We observed that the best performance model for in both cases, is the convolutional recurrent neural network, both in the Capitan and the sales datasets. And data augmentation, we see that it is the best option to converge and to also stabilize our performance during training. I display here an example of prediction. We've got on the left side the image that has been transcribed. This is a test sample of an 8% symbol error rate. And on the right side, we can see the transcription with the type of errors that have been done by the network, and also we highlight with different colors, being pink, the correct shape and wrong position classification, the yellow one, the correct position and wrong shape classification, and the red one, the complete misclassification or symbol avoidance. The network hasn't read the symbol and hasn't predicted yet. So as conclusions for this work, we have presented a layout analysis-free end-to-end transcription system that deals with monophonic full-page optical music recognition. It reads based on score unfolding, so it doesn't require layout or document analysis for it. And we don't also need to label that in our datasets. It presents competitive results against the state-of-the-art models, although there is a trade-off here between precision and labeling cost. It is also able to avoid noisy information that it is not labeled in the image, such as lyrics, for example. Both corpora had lyrics on them. And we observed that the tendency of putting sequence processing improves the overall performance of the models, also data augmentation. As future work, our model is limited for monophonic scores because the leading procedure doesn't fit with polyphonic scores. So we need to study new methodologies and data structures to handle polyphonic documents. The datasets presented have short sequence music scores. So we believe that the transformer approach could be an interesting competing implementation for common Western scores that have more symbols. And also there is a dependency on data amount. We have seen that data augmentation stabilizes the overall performance of the model. So we think that we have to study also the use of transfer learning and data synthesis to learn generic models, and also the implementation of self-supervised learning to do generic music reading for these systems. And that's all. I hope you got interested, and thank you very much.
Thank you, Antonio. Great presentation. So now we can, since Antonio was on time, we can have 2-3 questions. You can raise your hand if you have any question. Yeah, Jury, you can go first.
Could you explain how do you deal with variable page size? Because I didn't quite understand how do you transfer the two-dimensional feature space from the convolutional layers into the sequential. Is the number of stuffs fixed, or how does that work, like in detail?
Okay, so the thing is that, yeah, it is this image. Yeah, I had to explain it a little bit quick because we have time constraints. So the thing is that what we do is to concatenate sequentially all of the feature map rows. So that's independent on page size, because what you only do is to reduce the image, and then you just perform concatenation with the available rows you have. So it is independent on size on that way. And as you only have transcription.
Can it happen that a single stuff is represented by multiple rows of features and those get concatenated next to each other?
Yeah, it could happen, because this is only relegated to learning. Yeah, I just put a simple example, but it could happen whatever, because this is dealt by backpropagation in this case. Yeah, the only thing we require is that when we concatenate features, yeah, it is read that way.
So it's the responsibility of the recurrent network to figure out these, to align it back together.
Yeah,
if I understand it correctly. Okay, so it's interesting that it works.
Just to follow up with that question is, can we assume that the error from the unfolding to be passed to the rest of the architecture? And how can you basically trace back? Because there's still some error being propagated or being accumulated at the end of that network.
Well, the problem of this, method, indeed, it is that we are only we have only the predictions, or our ground truth is only the transcription of the full page. So the only thing that we can do is to rely on the CDC posteriogram that we obtain. So with that, we could try to make an approximation of where symbols have been located in the horizontal axis when reshaping it into the full page. But the thing is that we cannot easily trace back that, because, as I have said, there is no layout analysis information. We are relegating this only to learning. So the only way that we can know that reshaping is not being performed well is because we are obtaining bad transcriptions or less accurate transcriptions. Because, yeah, we don't have any layout analysis information. The only thing that you can do is to convert the CDC spectrogram into into the feature map, and then rescale it into the music score, and then you will have an approximate position where the node has been predicted, the symbol has been predicted. Yeah.
Thank you very much. Alexander?
Yeah, just a short question. So did I understand correctly that both the number of staves as well as the points within the full extracted feature map where to split it are learnable parameters from the network?
No, they are not. They're not.
Okay.
It is only learned by transcription. The thing is that they are not learnable parameters because the network cannot determine the number of staves. But the thing is that it learns how to align them. So ideally, the thing that the network does is to detect where are the staves and to reshape them during convolutions in order that each stave are somewhat aligned with each row of the feature map. So then when reshaping it, the transcription can be performed reading from left to right. But they are not learnable parameters because indeed both corpora have variable sizes of, variable number of music staves.
Right. So that means in turn that this figure that you're showing right now is kind of an ideal scenario, what the network would ideally learn to kind of do this kind of transformation. However, you don't know exactly what is going on within the score unfolding operation because this is just a learned convolutional block. So you assume that it's doing this because you're getting the correct transcription, but actually you leave it as a black box.
Yeah, we leave it as a black box because we don't know exactly what the network is actually learning. And it could be perfectly just half of the stave in the first, well, it could represent half of the stave in one row and the other half in the other one. As they are concatenated, they can be read from left to right. So that would be also a viable operation. But the thing is here, for the sake of visualization, we have put only a simple scenario.
Okay, thanks.
Thank you very much. We can leave the rest of the questions for the panel.